If you ever seen a puddle of water disappear on a hot summer day, or PhD students' tears drying from their face, you observed a powerful energy transfer, water evaporation. Evaporation not only dries out puddles and tears, but it also delivers snow to mountains and fuel hurricanes. It is therefore an incredibly powerful source of energy. Since 71% of our globe is covered in water, the potential utility of harnessing power of water evaporation is huge. But how can we harness this evaporation energy? Well, we need materials that are able to transfer the energy of evaporation into mechanical motions. These materials are known as water-responsive materials, and they swell and contract in response to changes in humidity. I want you now to imagine that you walk through a forest on a hot summer day, and suddenly it starts to rain. You look around and you observe pine cones closing and spider silk shrinking. These are natural water-responsive materials. Although they are very powerful, they are also very complex, and their mechanics are poorly understood. So the idea of creating synthetic materials that are powered by evaporation sounded exciting and very challenging to me 5 years ago when I started my graduate program. But since I work at the Advanced Science Research Center and one of my advisors is an expert in nanotechnology and another in evaporation energy, I thought I had a pretty great setup to give it a try. My goal was to create water-responsive material, understand how it works, and how it can be utilized to develop new ways of using evaporation to power movement. In my research, I work with simple chains of protein building blocks. Because they are simple, their properties can be tuned and optimized to form morphing structures powered by evaporation. After designing and trying several combinations of these building blocks, I noticed that a particular design was strikingly different than all the others. It formed large crystals, and when I placed them under the microscope, I observed that when the humidity was changed from low to high and the high to low, these highly organized structures, as you can see on the right hand of the slide, contract and expand. They are therefore water responsive. As long as the humidity changes, the material can swell and contract in infinite cycles. This repetition is crucial because it constantly takes the evaporation energy and transforms it into movement. By precisely studying them, I was able to identify the factors that control the movement of these structures. My work provides insight into mechanism of water responsiveness and can serve as design criteria to develop not only efficient actuators for energy harvesting, but also for soft robotics or artificial muscles. Thank you.